Welcome to EF5 Overview. This is Module 1.3 of EF5 training offered by the University of Oklahoma's Hydrometeorology and Remote Sensing Group. My name is Ray Clark. Thank you for joining me today. So we're still in day one of the training. This is actually the third module of a total of 7 in this series. You should have already watched the modules for the welcome session and also the introduction to hydrological models. Now we're going to talk about an overview of EF5. After this would be the DEM derivatives module. So if you haven't watched those first two, we recommend you go back and do those first, and then rejoin us here in video 3, EF5 overview. So let's talk about some features of EF5, and let's also review what we already know about EF5 from the first two modules. Again, EF5 stands for the Ensemble Framework for Flash Flood Forecasting. It's a distributed hydrological model that takes advantage of multiple computing cores, parallel computing strategies, and other modern technologies in order to produce faster simulations. EF5, as the name implies, supports ensemble forecasting. So there are multiple model cores that currently exist in EF5, and more are consistently being added to the program. Each core contains slightly different physics, so it models different processes inherent in hydrology in slightly different ways, and that results in different scenarios or different solutions for a particular set of input data. And it also helps to save time because that means that you can generate one series of input data, one series of precipitation, one series of PET, one control file, and then you put that into EF5 and it runs it through all the different models at once and gives you a bunch of different solutions. It's also cross-platform. This training is designed and done in Microsoft Windows, but it was originally developed on Unix-like systems, and so that includes many different Linux distributions, and also Macintosh OS X. You can run EF5 on those computer systems if you so desire. EF5 is also user-friendly. As you saw in the Wang2 example, if all of the required data has already been provided and an example set up, running EF5 is as simple as just double-clicking the icon on the screen. It's also a very flexible model that can accept multiple input data formats. And if something goes wrong, EF5 includes helpful error messages that identify exactly what the problem is, so that you don't have to spend a lot of time tracking it down like you might have to with other pieces of software. EF5 also includes coupling, so runoff generation and flow routing are coupled together in the model just as they're coupled together in the real world, and so that helps to make the simulations more realistic. And EF5 output could also be used to study atmospheric water, surface water, and subsurface water, so it really does encompass basically everything there is that you want to study in hydrology. It's also a very scalable model, so inside each grid cell, the water storage in the soil is modeled, and so that means that you can think of those cells as self-contained. Each one is kind of its own model, and that means that the number of cells and the size of the cells can be specified by the user without adversely affecting the model accuracy. Instead, all it really affects is the amount of time it takes the model to run. And so that means that EF5 is suitable for flash floods at small scales, riverine floods at very large scales, or even global forecasting. And in fact, EF5 is being used currently in all of these different applications in various areas of the world. So, the model structure for EF5 is broken down into 2 main sections, the water balance and the routing. So you can see on the block diagram on this slide, we have forcing, or the input to the model, and then we have output coming away from the model, and there in the middle is EF5, and everything inside that box is part of the model. And so those 2 components, the water balance and the routing, are needed for any simulation. The water balance concerns the water inputs and the outputs for each model cell. So recall that when we initially started talking about the water cycle, we said that water was neither created nor destroyed. Water in equals water out. And so the inputs, the precipitation, the upstream runoff, and the interflow, those equal the outputs, which are the runoff and the interflow that's being routed downstream. And routing determines how quickly those outputs will travel downstream. So you can think of water balance as referring to water amounts or water quantity, and routing dealing with water speed and where water is. Right now, EF5 has 2 options for the water balance with another under development. So right now, within the water balance, you can select 3 different choices. There's CREST, which is kind of the default option that we're going to be using throughout all the training examples. There's also the SACSMA, which stands for Sacramento Soil Moisture Accounting Model, and that's actually used by the United States National Weather Service, but also many other entities, agencies, and partners around the world. And then a third version called HIMOD, which is currently in development here at OU Hydros. There are also 2 choices for routing, kinematic wave, which is used in all the training examples and sort of serves as a default. And then there's also a second routing assumption that can be used instead, which is called linear reservoir. and that's currently in development and testing. And then other available model components for areas with a lot of snowpack or where a lot of water is stored on the top of mountains. The Snow 17 model is incorporated into EF5. And then there's also a simple inundation model or a bathtub model that basically just fills up from the lowest possible point until all the water has been exhausted. So that could help to be used in flood inundation modeling and flood extent modeling as well. The EF5 control file tells the model what to do. It consists of several blocks, each of which starts with a bracketed statement. And so the types of blocks include the basic block, precip forcing, PET forcing, gauge, and basin, just to name a few, and just to name the ones that are visible on this slide. And each one of those little areas outlined in red boxes, that represents a separate model block. And so then each block contains information within it that's all relevant to that particular piece of the model. So in each bracketed statement, you never change the type of block. In other words, precip forcing is always precip forcing. Gauge is always gauge. But if there's a second word to that block, that's the name of the block, and you can't change that. So in this case, the precip forcing block is named TRMM, T-R-M-M. You can change the name of the precip forcing block as long as you keep that name internally consistent throughout the entire control file. The other names of the blocks on this particular page, the PET forcing is called FuseNet, the gauge is called Chukka, and the basin is called Wingchu. So that gives you an idea of how the blocks are named and what the structure of the control file is. The basic block contains 6 pieces of information. There's DEM, DDM, and FAM, and those 3 things are file paths, and so they need to point to wherever a grid is located that contains that information. So we'll learn more about all of these in Module 1.4, which is coming up after this current module. But for now, just suffice to say that you can put those files wherever you want on your computer as long as the control file accurately reflects where they're located. Otherwise, the EF5 will give you an error. And the error is no big deal. It'll just tell you, could not find DEM or could not find FAM. And as soon as you see that, then you know to go and check the control file and make sure that that file path is entered correctly. The projection option, or PROJ, that's the map projection associated with the topographical information. So in this example, we're using an unprojected, or we're using just a latitude longitude grid, so we call that geographic. Esri, DDM, and self-FAM, those are options related to how some of the topographical information is encoded and what formats are used. And again, there'll be more on all of this in Module 1.4, and also in the EF5 README file, which is available as part of the training package. The precip forcing block in this example is named TRMM, and so this block consists of information about the type, structure, and location of the precipitation forcing to be used by the model. So you have the type of file, the units that the precipitation is stored in. Frequency is an important one. That tells EF5 how frequently a new grid is available. So in this case, we have a D for day. That means there's 1 grid per day. Location, that's the file path to where the precipitation is located. And then the name is a really critical one. For precipitation and for PET, EF5 needs names that include date and time information. So in this case, the YYYYMMDD, that stands for year, month, and day. So EF5 goes through and it knows that each file is named TR 2015-0101, for example, 2015-0102, etc. And we'll talk more about precipitation in Module 2.1. The PET forcing block works identically to the precipitation forcing block. In this particular example, there are a couple of interesting differences. One of those is the frequency. In this case, we have a lowercase m, which stands for month. So that means that there's only 1 grid per month, so there's only 12 total. And again, here we also want to make sure that the name consists of some sort of date information. So here, MM stands for the 2-month date. So we have PET 025.01, PET 025.02, and etc. And again, we'll talk more about PET forcing in Module 2.1. And then the gauge block. The gauge block consists of information about the gauge. You can run EF5 for multiple points or multiple gauges all at once. In this case, we're going to keep things simple. So we only have 1 gauge for this example. But for each gauge, you need to tell EF5 where it's located. The easiest way to do that is with the longitude and latitude in decimal degrees. You could also do that using alternate options called cell X and cell Y. So if you're working in grid cell space and you just want to tell EF5, my gauge is the 50th cell to the left and the 25th cell to the north, then you use cell X and cell Y. But for most applications, it's probably easier to just use latitude and longitude. OBS, or OBS, that's the file path to a location that holds a file containing the observations. That's not required for simulation, but it is required for calibration because the model has to have something to compare the simulation against. The basin area, that's the contributing area of the gauge in square kilometers, or the amount of land area that's draining into that gauge. And then output TS stands for output time series. And so here we've listed that as true, and that tells the EF5 that we actually want a file to be produced for this gauge. The reason why this option is important is, remember, you can have more than one gauge block. So if you wanted to run EF5 over 100 gauge blocks all at once, but you really only wanted to see the output data from one or two, that's why you have that output time series flag. There's also something called the basin block, and so the basin block is basically a collection of gauge blocks. It's not a physical basin. So again, think of that example where we might have 100 gauges all together. You could put 50 of those in one basin and then 50 of them in another basin if you had some sort of logical way that you wanted to distinguish the two. So in this case, we only have one gauge, and so the basin block is very simple. It's just basin Wangchu, and then the gauge is Chukka. And remember, the gauge name here has to refer back to the name of the gauge block that we just talked about. We also have model parameters that we're going to start to discuss. Each component of the model has its own set of parameters. So that means there's a set of parameters for the routing, and there's a set of parameters for the water balance. So let's talk about the crest water balance first. There are 6 parameters, and they're like the knobs on an old-fashioned car radio. They allow us to tune the model to get better simulation, just like you used to tune a radio to get better reception from a particular station. So the crest param set block, in this case it's called Wangchu. The gauge is called Chukka, so the parameters have to refer back to the gauge that we already named. And then we have 6 lines, WM, E, IM, KE, FC, and IWU, and those are abbreviations for the various parameters, which we're going to talk about more later on in the training. And just some brief descriptions of these. WM is the maximum soil water capacity. B is the exponent on the VIC equation, which is that curve that we talked about. IM, or impervious area ratio, that's how much of a particular region has land covered with concrete and asphalt and other impervious structures and materials. KE is a conversion factor from the PET that you get from the forcing grid down to what you think the actual evapotranspiration is, so it's always going to be less than the potential evapotranspiration. We have the soil saturated hydraulic conductivity, and then IWU, which is an initial parameter or something that the model uses when it's first warming up. If you want to specify different parameter sets for different gauges, basically all you do is you copy that crest param set and then you paste new blocks in after it. So that's why basins are really nice, because they allow you to specify for a set of gauges all the parameter sets. So if I have 100 separate gauges, but I only maybe want 2 or 3 parameter sets, I put those 100 gauges into 3 different basins and then I specify the parameters for those basins. And again, we'll talk more about parameters in Module 2.2. The KW param set, KW is short for kinematic wave. In this case, it's called Wangchu, which is the name of the basin. So we have the gauge underneath, which is the name of the gauge block for those parameters. We have TH, which is a threshold. That's the number of grid cells that have to flow into another cell for that cell to be considered part of a river channel. We have under, which is the interflow flow speed multiplier. Leak I, which is a parameter that tells us how much water leaks out of a particular water bucket at each time step. ISU, which is an initial value for the interflow reservoir. And then we have alpha, beta, and alpha naught, which are used in an equation in the kinematic wave assumption. And that equation is stream flow equals alpha times cross-sectional channel area to the beta power. And so alpha and beta are for channel routing, alpha naught is for overland routing. Then we have the task block, which is a really important one. This consists of basically all of the programmatic or programming preferences that you have for EF5. So these are the preferences for how you want EF5 to run. So style is probably the simplest of those. In this case, we're using Simu, which is short for simulation, but there are other ones for calibration and other options besides that, as you can see in the README file. Model, that tells EF5 which version of the water balance we want to use. So in this case, we are using Crest. There's also Sacramento. For routing, you can have kinematic wave or linear reservoir. And then in the basin line, that's telling EF5 which basin to run in this task. So in this case, we're going to run basin Wangchu, which has parameter sets Wangchu and has gauge Chukka. So all of these things are kind of tied together. And task block is sort of at the end, and it's the one that ties everything together, takes care of everything right before the model's about to run. Precip and PET, Those are just the block names from up above, higher in the control files. So remember trim and FuseNet, we already discussed those. Output is just a folder where we're going to store the output from the model. Param set and routing param set, those names should correspond with the names of the parameter blocks you want to use. And then finally at the end we have our timing information. So here we're running EF5 every day, so that's why we have 1D in our time step line. And then we have time begin, time warm end, and time end. And those are basically just date and time codes that tell EF5 when to start the simulation and when to end the simulation. Time warm end is optional. That's the time when the warm-up period for the model ends. So everything before that time doesn't count towards you in the end. Everything after it counts as part of the actual simulation. So we've so far just described kind of very basic options, very basic requirements, but the model has additional components that will be considered in the rest of the training. They're in the README file. There are many, many more options that we haven't discussed yet. But for now, let's kind of take a step back from that for a second and discuss two more general but still important modeling concepts, model warm-up and model states. So if you recall from the last module, 1.2, we had a bucket metaphor, and we talked about how precipitation or water is transferred from one bucket to another, and in what order those buckets change, and how those buckets can move back and forth between one another. But now we want to imagine a time before the model has started running, and all the buckets are empty. And we need to know when the model first starts how much water is in all those buckets to start with. So you could do that, at least for the soil, by going out and measuring soil moisture. You could do it by measuring the health of plants and how much water they're actually storing. You could go take some gauge measurements on a river and find out how much water is in the channel. But for some of the buckets, they only exist in model space. They correspond to real things, but they're not things that we can actually measure. They only exist in the model. And so for those, we need some other way of figuring out how much water is in the buckets. The simple answer is we usually don't know the answer to this question. So we use some sort of guess. We guess how much water is in there, and we call that the initial conditions or the initial model states. And these estimates aren't ever perfect, but that usually doesn't matter because we have something called a model warm-up. Here's how it works. So you're going to assign initial conditions to the model using parameters. And remember, we had several parameters we mentioned that started with an I, and that I stands for initial. So let's say you tell the model that the surface water, the groundwater, the runoff, and interval buckets, they're all half full. Likely, that's not a perfect guess. That's likely not going to be 100% accurate. In fact, we know it's not going to be 100% accurate. But we know that it's more accurate than saying they're completely dry, that there's no water in any of the buckets, because we know there's at least some water stored in all of the plants and stuff. Otherwise, they wouldn't be alive. So now you're going to let the model run for some specified warm-up period until those buckets reach equilibrium, or until those buckets get closer to reality. And then, after that, you're going to use only those simulation results to calculate your statistics. So everything in the warm-up period, everything before time warm end in the EF5 control file, that doesn't count. That's all just the buckets getting up to the right point and leveling off and everything getting where we want them to be. Only the stuff after the warm-up is complete actually counts towards the statistics. So without knowing it, actually in that first example we just ran, we had a short 1 month warm-up period. The simulation began on the 1st of January 2001, but all our hydrographs began on February 1st, 2001. And that's because we let the model warm up for that first month before we started to count the results. And you can actually see that here on slide 27 in the screenshot of the control file. Time warm end was 2001-02-01, January 1st, 2001. And then you see, or February 1st, 2001, excuse me. And then you can see on our hydrograph that it actually did start on February 1st, 2001. And those results from the warm-up period, they're not output because they would not typically be used for any analysis. So I'm not going to do this right now, but if you want, you can go into the Wangju example, open the control.txt file, and add a hashtag, or as the older generations now call it, a $, and add that hashtag right in before time warm end. And that turns that line into a comment, which means that EF5 is going to read right past it. It's going to ignore it. So now EF5 thinks there's no warm-up period. And you can go ahead and save the control file and then double-click the appropriate batch file. So remember, if you're running 32-bit Windows, you want to do the 32-bit batch file. Otherwise, do the 64-bit one. Now, open the results that are in your output folder. And when you open those up in Excel, you should notice how small the values in January 2001 are compared to the observations. The discharge in this screenshot are all 0 or 0.01 or 0.02, and our observations are up in the 25 to 27 range. So using the instructions from module 1.2, and just to practice my hydrograph making skills, because again, that's always an important skill to have, I went through and created a new hydrograph without the warm-up period. So that's on the lower left, or on the lower right, excuse me. The old one from the last module is on the lower left. And you can see in the areas highlighted with the blue boxes that we now have a slightly longer period at the beginning of the hydrograph where there's not much happening. The values are extremely low. And that's because, again, we don't have a warm-up period now. But to see this more extremely, let's start a simulation during the rainy season. So again, if you want, you can go into the control file and change the start date to August 1st, 2001. When I did that and went through and ran the model, I got the result at the lower right. And so you can see in the big blue box that the red line starts way at the bottom at 0, and it takes a couple of weeks until it gets up to a level that looks somewhat accurate. And if we zoom in on that, sure enough, that's what you see. It takes until about August 12th or 14th, maybe all the way to August 18th or 20th, before the model is actually, which the model is in red, before the model is actually getting close to where the observations indicate it should be. So that suggests that a warm-up period for this size basin is required about 2 weeks, and a month would be pretty safe, and a month is what we had initially. Running without a warm-up period, it risks you including bad data and bad results in the beginning of your simulation. So that's why you always want to make sure that you have a warm-up period, especially for basins that are larger. The larger the area the basin encompasses, the longer the warm-up period is needed. And sometimes this is something that you just have to experiment with as you calibrate the model and change the parameters and change other settings. You just need to make hydrographs and look at it until you see what looks good and what looks appropriate. Now, this brings up another important point, which are model states. So let's imagine a different situation. Let's say that I'm in an operational forecast center and I'm running the model every day at the same time, every day at 7 or 8 a.m. on Wangchu Basin when new rainfall data comes available, when it comes from the satellite, from a rain gauge or whatever. But I don't want to waste my computer time starting the model over at the beginning and running through that warm-up every single day. Now, I know for this example, EF5 was really fast, but let's imagine that we're running the model over all of Asia, and it takes a day to run for just an hour. And so in that case, we would have no choice. We would need to save our model states. So what we do is at the exact point when the warm-up period ends, we save the model states. So we save the stream flow at every point. We save the precipitation. We save the actual evapotranspiration. We save the soil moisture. And we keep all of that, and then the next time we decide to use the model, we use those as the initial conditions going forward. That means that we only have to run the model forward in time from the point when the states were saved. So let's say that I've been running this hypothetical model over Asia every day for the last 2 years, and I know that it requires a warm-up period of 6 months. If I didn't have model states, I'd have to be running that model through 6 months worth of data just to get the new day at the end every single day. But if I save the model states at the end of the previous run each day, now I'm only running the model forward in time for a day, which is literally, it's a tiny fraction of the amount of time that it would take otherwise to run. So, just an example we give in the PowerPoint, you could potentially go from taking 6 hours or even days to run down to getting forecast updates every 5 minutes or every 10 minutes or even every 3 hours as new satellite preset comes in. It's a much, much more efficient way of doing things because now you're not running the model through all that rigmarole every single time. Now you're just saving one simple set of model states and then going forward from there. This technique has been employed in one experimental example where OU and NASA have partnered together to produce forecast stream flow and soil moisture in the nation of Namibia, which is located on the southwest coast of Africa. So on the Okavango River Basin upstream of the town of Rundu, we actually have real-time and near real-time outputs from various parts of EF5. The web address for that is flash.ou.edu/Namibia if you're interested in seeing more of EF5 in action on an everyday basis. And each new set of forecast rainfall coming from either a weather model or estimated satellite rainfall coming from satellite can be added to the previous model run without warm-up because we save those model states. So the results are available very quickly. As soon as the rainfall is available, you run EF5, you generate the products, and then your new forecast is available. And so that's a very powerful technique. So let's recall example 1. We produce this hydrograph shown here, and now we want to know, is this a good result, a bad result, or somewhere in between? We can look at it visually, and we can try to see, yeah, the red and black match up pretty well, or they're perfect here, and they're a little bit off here. But just talking about it in those terms, while helpful, is not all we need. We need to put some statistics to it. So that's what we're going to do now. So we're going to talk a little bit about model evaluation indices. In general, the result is better the closer the match between the black and the red gets. But how could you tell between 2001 and 2002 which of those two sides of the hydrograph is better? In this case, it's actually difficult to tell, and so that's why we have model evaluation indices. So the first one is bias. Bias can be thought of as a shift up or down in a hydrograph. The lower right hydrograph has some high bias. What I did was I basically went into Excel and I multiplied every model value by 2. So I basically doubled it, added 100%. This is a conditional bias, so the higher the original value now, the greater the bias, or the greater the amount of extra stuff has been added. And so to give you an idea of the statistics, the difference between these two, at the lower left, the original hydrograph, we had a bias of 30%. On the right, our hydrograph now, after I've added that bias, is 159%. The CC and the Nash, those are two other model evaluation indices that we'll talk about in just a moment. But the reason they're shown here is to show you that bias and correlation coefficient are mostly independent from one another, but Nash is not. It requires both the bias and the correlation coefficient to be good or adequate. Bias could also be constant or non-stationary, so you could have a bias of 4 cubic meters per second and just add 4 onto every single thing instead of doubling it, or you could have one where it subtracts it. There are different ways of looking at bias. It's usually expressed as a percent. The way we calculate it for the training is that when bias is positive, that means that the model is too high. When bias is negative, the model is too low. And we like bias values close to 0. Again, if it's the vertical displacement from one another on the graph, we want those two things to line up perfectly alongside one another, and that's when our bias is 0. So mathematically, we promise we don't have a lot of equations in the training, but we do have a few in this module. This is how you calculate bias. It looks like a really ugly, awful equation, but we're going to break it down step by step and find out that it's actually pretty simple to calculate. So that first term, sigma r simulated, that's the sum of all of the simulated stream flow values. So you just add up that whole column in Excel. The other term, the sigma of all of the r sub observation values, that's just the sum of all of the observation values in that column. Really simple. So we're going to now actually go through and calculate bias. So the first thing we're going to do is go into EF5 training. Now I'm going to go into my examples folder, and then into Wang Chu, and then output. And you may not have done this, but earlier whenever we were making the hydrograph, I saved my file as an Excel sheet, .xlsx. You might have just kept the original file as a CSV. Either one will work, but what we need to do is go ahead and fire up Excel. So I'm going to do that, and I'm going to go ahead and open up a file, and you might recognize this from earlier. We have the hydrograph that we made, and so I don't need that right now, so I'm just going to push it off to the side, and I'm going to deal with all of these different columns of data, and I'm going to start to calculate bias. So you could do this in any column you want within the spreadsheet, but I'm going to go ahead and follow along exactly what I have in the PowerPoint on slide 43. And so I'm going to basically start off by calculating the bias. So here in cell J2, I'm going to have the sum of simulated values. And then in K2, I'm actually going to calculate this. I'm going to do equals, and then I'm going to have a parentheses. Or actually, I don't need a parentheses. I'm just going to say sum, and then a parentheses. And for this one, I want to add up all the simulated values. And those are in column B. So I'm going to do B2 colon B700, close parentheses, and hit enter. And I get a value of 90,073.04. Just below that, I'm going to do the sum of observed values. And this time I'm going to say equals sum and parentheses, and I'm going to do C2 colon C700 close parentheses. And I get a value of 69,441. Now I'm going to subtract those two things, and that's going to give me the numerator in that big, ugly equation. So on my spreadsheet, that'll be K2 minus K3, and I get something just over 20,600. Now I need to divide, and I'm going to divide that subtracted value, K4. And Excel, you use division by doing a slash. So I'm going to do K4 slash, and then I'm going to do the observed values, which is K3. And I get 0.297. And then I multiply by 100. So I'm going to take K5 and I'm going to do an asterisk multiplication, and 100, and I get 29.7, or 30 when you round up. So our bias for this example is 30%, which means that on average the model is 30% higher than the observations on average. Correlation coefficient is a little bit different. That measures the agreement between the simulation and the observation time series from side to side rather than up and down. So you can think of it as sort of a time matching thing. Now, if there are any mathematicians in the audience, that's not exactly true, but for the purposes of this training, it makes things easier to understand, so that's how we're going to think about it. Bias is an up and down movement in the chart. Correlation coefficient is a side-to-side movement in the chart. Correlation coefficient can be measured. You have a negative correlation if you're all the way at -1. You have a perfect positive correlation if you're all the way at 1. And so we're looking for values of something close to 1. 1 is desirable. And so what I did in this example was at lower left, I ran through our original hydrograph, 30% bias as we just discovered, and the correlation coefficient was 0.86, which is pretty close to 1. That's pretty good. Then I did a phase shift, and I basically moved one of the time series forward in time. And so now the two series don't match up at all when you look at the lower right. And sure enough, our bias is still the same. That didn't change. But now the correlation coefficient is negative, and that NASH, NSCE, that we haven't really talked about yet, that also got negative, which is bad. So this is just reiterating what I just mentioned, that correlation coefficient is more of a side-to-side shift in the hydrograph rather than an up and down shift. So the way to calculate correlation coefficient, it looks fairly complicated, as you can see from that equation, but it's actually pretty simple. Correlation coefficient is used frequently in a lot of math arenas and science arenas, and so Microsoft Excel actually has a built-in function for that. So over here in my Excel window, I'm going to type in correlation coefficient, and I'm going to do that in cells J8 and K8, and I'm going to type in equals, and I'm going to do CORREL, and you can see Excel is trying to autocomplete Correl for me, and it says returns the correlation coefficient between two data sets. I'm going to do a parentheses, and then I'm going to say B2 colon B700, comma, C2 colon C700, close parentheses. And when I press enter on that, I get 0.855, or when we round it, 0.86, like you see in the PowerPoint. Now we're to NASH, or NSCE. Nash-Sutcliffe coefficient of model efficiency. Now you see why we call it NASH, because the full name is quite a mouthful. It exists on a scale from -infinity to 1. And so when NASH is greater than 0, mathematically, what we're saying is that the model has more skill than if you just use the average stream flow from the observations over the period of the simulation. So when you have a NASH that's positive, or greater, as we say, greater than 0, then that means that you're actually more skillful than just using the average as your forecast throughout the entire period. On a hydrograph, you can visualize NASH as the amount of space or distance between the observations and the simulations in a general sense. It doesn't really have a side-to-side or up-and-down component like the bias and the correlation coefficient do. And the equation for NASH is down there at the bottom of slide 48. And again, it looks a little bit nasty, but Excel has some built-in functions that can help us break this down and make it easy to understand. So let's get overbar R obs first. The overbar means average. So we're going to take the average of all observations. And here in Excel, I'm going to do that in column I. So I'm going to call this average of observations, and I'm going to type equals average, and then I'm going to do parentheses, and I'm going to do C, and then a $sign. And that $sign tells Excel that when we decide to fill all of the values downward, it's not going to move things with the fill. So that may sound a little confusing, but just trust me, you want the $sign. So C $2, colon, C $700, close parentheses. And you should get a value of 99.34. And then most of you probably know how to do this, but if you aren't really experienced with Excel, we need to copy this thing down through all 700 columns, or all 700 rows, excuse me. If you did that manually, it would take a really long time. So instead, I'm going to move my mouse over to the very bottom right corner of this cell, and my mouse is going to turn into a little black plus sign. And once it does, I'm going to double click that, and now I have 99.34 going all the way down my screen. That's exactly what I want. Now I want to calculate the numerator, so I'm going to type in NASH numerator, and I'm doing this in cell J10, and then inside cell K10, I want to get the square of the sum of the differences between each observation and each simulation. That may sound a little bit complex, but all you need to know is that the way Excel does this is with something called sum x, m, y, 2, and you can see it auto-completes that for me. Open parentheses, and it's telling me it needs array x and array y. And so in this case, array x is going to be your observation, so that's C2 colon C700, comma, B2 colon B700, close parentheses. You press enter, you'll get some huge number that's around 3 million or so. The number itself is not important. What we need is the end value. Now we're going to go and do the same thing for the denominator. The Nash denominator is also the square of the sum of the differences, but this time it's between each observation and the mean observation. And the mean observation is that thing we just created in column I. So let's do it again, equals sum x, m, y, 2, open parentheses. And this time your x is going to be your observation, so C2, C700, comma, and we're going to do I2, I700, or wherever you put that list of average observations. And you should get something around 6 million, 6.2 million or so. Now we're going to put it all together. So Nash is going to, I'm going to label that in cell J12, and then in K12, I'm going to say equals 1 minus parentheses. I'm going to take the numerator K10 divided by the denominator K11, close parentheses. And I get 0.515, or when you round it, 0.52, which is the Nash that we've been talking about. So back to our original question, was the model output good? Well, the correlation coefficient, 0.86, that's very good. On this scale, they were getting up close to 1, which is perfect. That's a really good correlation. The bias is higher than we'd prefer at 30%. We'd like, of course, something closer to 0. And the Nash is pretty good as well. This, of course, is a calibrated example. And so when you calibrate the model, you want values up at 0.5, 0.6, 0.7, maybe even 0.8 if you're really good. For uncalibrated models, you can have much lower values of just above 0 somewhere. But the verdict on this is for not doing really any calibration or very little calibration, this is a really good result. You could do more calibration to make the model output better, but this is a pretty good hydrograph on the whole. So that concludes the EF5 overview. The next module is DEM derivatives, in which we'll actually get into QGIS. We'll get our hands dirty with actually messing around with DEMs and FDRs and flow accumulation grids and all sorts of other things that you'll be introduced to. You can find that next presentation in your EF5 training folder and inside the presentations folder. And you can also join us for the video of the 4th module. But until then, if you would like to review some of the references and other materials associated with this module, you can check out the EF5 README, which is available in the documents folder of EF5 training. You can also read training doc number 2, which is on hydrological model evaluation. And if you'd really like to learn more about the mathematics behind why the Nash works so well for what it does, you can read Nash and Sutcliffe's original paper from 1970, which is also in your documents folder. So thanks very much for being with us, and we'll see you in the next module.